Right, we're carrying on with this equilibrium. Right, let's crack on. Let me just start again. This sign here shows that the reaction is reversible. It can go in both directions, right? That there is delta H, and it's the change in enthalpy. Right, another word for enthalpy you can say is heat or energy. Or heat energy. This here we said was a delta, and it's a capital letter D in the Greek language. What else is that? Right. From here, in your mind, you draw a line straight down and you say 1 mole here plus 1 mole here. Why is it 1 mole? Because you've got in front of here, they've not written it, but there's a 1 there and there's a 1 there. I'm not interested in what these are. All I know, I've got 1 plus 1, so I've got 2 moles on this side. Now on this side I've got 1 mole. So I've got 1 mole here. Now the side with the most most moles has got the higher pressure. So this is high pressure. I'm gonna write pressure, and I've got low pressure on this side. Right. Now if you look at this minus, that tells you it's an exothermic reaction. So the negative or negative delta H equals exothermic reaction. That means it loses heat to the surroundings. Right, what we need to do is, so from there we can make the decision that, so remember this is, let me just draw it in green. So look, this is the line, and on this side here, it's high temperature. This side here is the low temperature side, right? The forward reaction, so I can say here, look at the language. So forward reaction is exothermic. The reverse reaction or backward reaction is endothermic. Right. It's in predict and explain the effect of increasing pressure. So remember what we said. We said if you, let's get this right. So we're just concentrating on, let me just highlight it. We're just concentrating on this side. Oh Right, we're concentrating on this side for pressure, this side for pressure. So they've increased the pressure. The system then wants to go to the opposite side. So it wants to go to the low side, right? So what they're saying, what's going to happen, the equilibrium, look at it as this arrow. What's going to happen? It's going to go to the low side. So what I can do in my mind, I can say the equilibrium is going to shift to the right. It's going to go to the right hand side. So the prediction is equilibrium will shift to the right, or you can say right hand side. And what was the reason? It's because this right hand side has got less moles. This has got, it's got 1 mole on this side, but it's got 2 on this side. So you say because it has less, you can say molecules or moles. We'll stick to, I don't know, stick to whatever you want, moles or molecules, whatever you want. That's it. That's your 2 marks. And it's as simple as that. You just, I'll show you this again. Right. So what we're doing is, let's go through all that again slowly. Look for this. Look for that sign there. So we know what that means. The reaction is reversible. I'm going through this really slowly, deliberately. The action is reversible. Right, so both forward and backwards reaction is taking place at the same time. Right, this delta H, we said the delta H means change in what? Change in what? What was it? Enthalpy. What did we say enthalpy was? Heat energy or heat. Right, so we've got those two. So I can put here reaction is reversible. And I suppose it's better to write it out with the second part as well. The reaction goes forwards and backwards. Right, delta H is change in enthalpy. And what did we say about this minus sign here? This negative delta H. Right, the negative delta H tells you the reaction is, what is it? The reaction is exothermic. It's only 1 marker. Right, complete the energy level diagram. It's exothermic. Exothermic. Okay. So let me go to the side again. If something is exothermic, I'm repeating all these words so it goes into your head. Exothermic means it loses heat energy to the surroundings. Right, so that means it will be at a higher temperature. Just remember that. Right, we want an energy level diagram, not an energy. I'm highlighting this profile diagram. Right, an energy profile diagram does something like this, or it'll do something like that. Right, this one is you draw a line, just even if you did it in the middle as a starting point, you write the reactants on this side. I'm just putting the word here. I'm going to go up and I'm going to copy the reactants. These are the things that we use to react. So let's do that. Reactants are 4NH3. You can put the symbols in if you want. You don't have to. Right. Now, because it's an exothermic reaction, the energy level, get this right, the energy level's here. It will go down. So what I do is, this is my line, so I just go down. Let me just do that. I go down, and about here, I can draw a line. It doesn't matter how long it is. And then what I do is I put down the products. So the products will be here, 4NO plus 6H2O, and that's that done. Right. I think let's copy this. Let me just do this. What I'm gonna do is copy this. Just bear with me 1 second. Right, I've got this now. So what I'm gonna do is I'm gonna draw a line down the middle here. So I'm just, you don't need to do this. This is just for us whilst we're learning here. So the first thing I look at is it's exothermic, because that's my negative. So this side is going to be the hot side. This is going to be the cold side or the cool side. That's step 1, yeah? Step 2, you've got 4 plus 5, you have 9 moles here, or molecules. You've got 4 and 6, you've got 6 molecules. Right. This means that this side here has got 9 moles, is going to be the high pressure side, and this side will be the, change that, and this will be the low pressure side. Now you've got that established, we can try to look at this. Right, we want to know, if I increase the temperature, what effect will it have on the rate of reaction? Look, this is what I always get wrong. Reaction and yield. So just concentrate on the reaction first. Increase in temperature will increase the rate of reaction. Adding a catalyst will increase the rate of reaction. So just remember, increasing the temperature and catalyst both increase the rate of reaction. Now the yield, that's this bit here. So that's that bit. Which way is that? Which way is the reaction going to shift? Is it going to shift to the left or to the Right, we don't know yet, so we'll have a look. So if you increase the temperature, the system wants to go back to its normal state. Oh my word, what's that? Normal state. Okay, so if you've increased the temperature, the system wants to decrease it. Let me get this. So the system wants to go to the cooler side, so it will shift to the left. So the system will shift to the left, and I don't know what to highlight that way. Is there an okay? Let's try with that. Right. This has got a low. If you go to the left every time, you will end up with a low yield. This will have a high yield. Right, okay. So it'll go shift to the left and you're going to end up with a lower yield, or it will, right, we're going to say decreased. So that's the word they want in there. That was just for us. Right, if we add a catalyst, does it affect the yield? No, just remember, a catalyst only increases the rate of reaction, that's that bit there, but it does not affect, so it's going to be, we're going to have to use the word unchanged. This is quite a good question because it does everything for you. So if you add a catalyst, it increases the rate of reaction, but it does not change the yield. So that would be a good one to remember. Do we need the Haber process? Not anymore, but what we'll do is we'll no. That'll come from the air anyway, but I'm interested in this question here. So right, what we're gonna do is we're gonna look at this. Can you see this plus? That tells you this is an endothermic reaction. What does that mean? It takes in energy. It absorbs energy. It absorbs energy from the surroundings. Oh my word. Surroundings. Right. This here, if you notice that it's negative, so we said that will be an exothermic reaction. That means it gives out energy to the surroundings. I've done it again. There you go. Right, we're going to just do a quick look at this here as well. You've got 1 mole here, 1 mole here, 1 mole here, 3 moles here. So this side here is the high pressure. This will be the low pressure. Now if you look at the bottom reaction, you've got 1 mole here, 1 mole here, so you've got 2 on this side, and you've got 1 here and 1 here, you've got 2 on this side. So they're both 2. So we don't know the effect. Yeah, so they're both 2 and they're both 2. So we're going to say that they're both the same. That's an interesting one, right? Predict what will happen to the equilibrium when in reaction 1, you increase the pressure. Right, so in reaction 1, if you increase the pressure, the system will go, let me get this, right, in reaction 1, if you increase the pressure, the system wants to go to the low side. So the yield, this thing here, will shift to the left. So the equilibrium shifts to the left. Right, why was that? Because there are fewer or less, we'll stick to the word moles, on the left hand side. That's the lower pressure side. Right, so the next one we're looking at is this. What will happen to the equilibrium in reaction to when the temperature is increased? So if you increase the temperature, the system wants to decrease it. So let's get this here. So this is exothermic. So what we're going to do is, what color can we use? No, let's use that. So we're looking at reaction 2. They're not talking about pressure, they're talking about that. So let me just remove this, and so we're just looking at reaction 2. Let's start that again. We're talking about temperature, right? This is exothermic, so this is the hot side of the high temperature side, this is the cold side. There's the equilibrium. So now if you increase the temperature, the system wants to go back to normal, so it wants to go to the colder side, it wants to go to the opposite side, so it'll go to the left, it will shift it to the left because that's the colder side. So equilibrium will shift to the left hand side. Why? Because we can just write it simple like this. Yeah, we can write that because the forward reaction is exothermic. You could also write the reverse or the backward reaction is endothermic. That'll be the same sort of idea. Predict what will happen to the rate of reaction when pressure and temperature. Pressure and temperature. Okay. In reaction 1. Right, let's get this pressure and temperature increased. So if you increase pressure, and this is the key thing you've got to look out for, it's the rate of reaction it's asking for. It's the rate of reaction, not the equilibrium now. So if you increase pressure, you increase rate of reaction. If you increase temperature, you also increase the rate of reaction. Right, that's good. Right, what we can do is we will, this is a very long one. This is actually good. It gets a bit tough at the end, but we'll keep going. So we'll do it in 20-minute slots. So yeah, that's fine. Right, we'll do it in the next video.